Hello, everyone. Let's get started with today's lesson, lesson 5 on covalent bonding. But before we get into covalent bonds, I just want to do a quick review on ionic bonding. To do that, I'm going to show you a simulation. Here's my screen. Try to share that with you. Okay. So, what I want you to remember about ionic bonding is that it's a strategy used by metals and nonmetals to get them full valence shells. The metal element is going to transfer valence electrons over to the nonmetal. As a result, the metal element will have a full valence shell now, and the nonmetal, by accepting the electrons, will also have a full valence shell. So that's the situation they want. They want full shells, complete octets, right? The trade-off, the problem here with this strategy is that the metal element now becomes positively charged and the nonmetal becomes negatively charged. And charged atoms by themselves are not good because it actually increases the potential energy state, destabilizing these atoms. So yes, they got full shells, that's great and all, but the charge on these atoms is bad, super bad. And so in order to make this strategy work, the two ions need to cooperate with one another and essentially say, hey, we can't coexist by ourselves. So let's bond together, let's form an ionic bond. I'm positive, you're negative. We can attract through an electrostatic force attraction. And by doing that, we will essentially offset the charge. Okay? We'll eliminate a net positive or a net negative charge. Okay? Now the charges are still there. They haven't gone away. It's just they're balanced out now, offset. And by doing that, they can exist together in a very stable, low energetic state. But they have to stay together. That's the only trade-off here, okay? So in this simulation, we're gonna kind of look at that. So we have lithium here, and lithium has one valence electron in its outer shell, right? And if it gets rid of that one valence electron, then its new shell will be full, okay? And remember, lithium is one of those elements that does not need 8 electrons in its outer shell. 2 is acceptable. We have a nonmetal over here that is chlorine. And chlorine, if you count the valence electrons, have 7 valence electrons. So it needs only 1 more to have a full shell. So what we're gonna do is we're gonna bring lithium and move it close to chlorine. And as it gets closer and closer to chlorine, there's going to be a transfer. Now watch for the transfer. Boom. Did you see that? There was a transfer of an electron from lithium to chlorine, right? And we just created a positive lithium ion and a negative chlorine ion, okay, as a result. The lithium, if you look now at its valence shell, is now full. It has 2 electrons in the valence shell. It's good to go. And the chlorine now has 8 electrons in the valence shell. It's good to go. The charges, though, are bad, but they're offset or balanced out by the bond that we just created between lithium ion and the chlorine ion, okay? So as long as they stay together, we're in good shape. Let's do another one. Let's do like the magnesium and the chlorine ones, okay? So magnesium, the one in the middle there is the metal, and it has 2 valence electrons. Again, if it gives off those 2 valence electrons, then it's in good shape because it will have now a new shell of 8 electrons. The chlorine atoms, both of those need 1 electron, right? And so magnesium can actually give up 1 electron to each one of those chlorine atoms, and away we go, okay? So what we're going to do is we're going to bring one of these chlorines over next to the magnesium. They're going to get closer, watch for the transfer, and boom, we have a transfer, okay? At this point, the magnesium has given up one of its electrons, so it creates a magnesium +1 charge, and the chlorine has a -1 charge, okay? So we're good in this sense that the positive negatives are canceling out, but the problem is that magnesium does not have a full shell yet. It still needs to get rid of one of its electrons. So the next chlorine is going to come by and get really close, and boom, magnesium can transfer its additional electron to chlorine, and now magnesium has a full valence shell. Count up the electrons, okay? Magnesium has an octet of 8 electrons. Each of the chlorines have an octet of 8 electrons. So everything is good to go. They just need to bond together and stay together to offset and balance out the positive and negative charges, okay? So that's just kind of a review that I wanted to kind of go over with you on ionic bonding. So let's get into actually lesson 5, covalent bonding now. All right, lesson 5, covalent bonding. Now, we've talked about ionic bonding, we've talked about metallic bonding, now covalent bonding. Covalent bonding is the last type of bond that we're going to discuss in this unit, okay? Now, think about this. Ionic bonding is between a metal and a nonmetal, essentially. Metallic bonding occurs between metal atoms. So what do we have left? Well, we have nonmetal bonding, okay? Covalent bonds are usually formed between nonmetal atoms, all right? And they're gonna form a unique bonding situation. They're gonna take a different strategy approach to completing their shells, all right? What we've been looking at is essentially the metal atoms, whether it's ionic or metallic bonding, the metal atoms are transferring or losing their valence electrons, okay? Even in metallic bonding, the valence electrons become delocalized, okay? But with covalent bonding, this is not going to occur. There's not going to be a transfer really of electrons that are going to occur in this approach or strategy. So what exactly is a covalent bond? By definition, a covalent bond is formed by the electrostatic attraction between a shared pair of electrons and the positive charge nuclei of both atoms, okay? So here, the nonmetals, remember, they're not wanting to give up electrons. They're not excited about that. So they have to come up with something else. And so if two nonmetals are going to bond together, instead of transferring to one another, they say, hey, let's do this. Let's share electrons, okay? Let's take our valence electrons and share them. And by doing so, then those shared electrons now belong to both atoms. And that will help them to complete their full shells or octet, okay? And as I mentioned here, that usually a covalent bond occurs with nonmetal atoms that are sharing their valence electrons, and this will complete their outer electron shells or valence shells, and they'll have a stable octet, okay? So let me show you some models of this idea. So what we're going to have is essentially two atoms here. And these two atoms are sharing a pair of electrons here, which is indicated by these two electrons. So essentially their orbitals are going to overlap, okay? And when they come together and they overlap the orbitals between these two atoms, they're going to share a pair of electrons. Now, every covalent bond shares 2 electrons and only 2, okay? Every covalent bond just shares a pair of electrons. And what we're saying is that one element or one atom is donating one of the electrons and the other atom is donating the second one. And this is a case that occurs most often. But there are some situations, some covalent bonds that are formed when one atom is going to donate both electrons that are going to be shared. So that does happen as well, okay? And we're gonna get into those situations later where one atom donates both electrons that are being shared between 2 atoms to form a covalent bonds. But right now, let's just say that one atom contributes 1 electron, the other atom contributes the second electron. They share those 2 electrons amongst themselves, and by doing so, this is going to give them a full valence shell, each particular atom, okay? So the nucleus of these atoms are attracted to both those electrons. And so both of those are essentially in competition or competing for these 2 shared electrons between each other, okay? Here's another look at it. So we have a nucleus of one atom, a nucleus of a second atom, and they are going to share these 2 electrons between these 2 nucleuses. And so this sharing of these 2 electrons is the covalent bond itself, okay? All right, so that really is a covalent bond in a nutshell, is the electrostatic attraction between 2 pairs of electrons being shared between the 2 nuclei, okay? Now, often we will use dots, okay, and as indicated in these models, dots between 2 nucleuses or 2 nuclei, and these 2 dots represents a covalent bond, okay? Or like in this case, between these 2 hydrogens, we have 2 dots here, and those 2 dots are representing, right here, these 2 dots represent the covalent bond itself, okay? So 2 dots in between 2 atoms is a covalent bond, or sometimes we use this hyphen, and that hyphen between 2 atoms also represents a covalent bond. Just remember that every hyphen represents only 2 electrons that are being shared between them, okay? And again, by sharing these electrons, it allows for both these elements to have a complete or full outer shell, okay? So keep that in mind as we continue our ideas with covalent bonding. Now, I want to talk a little bit about energy and covalent bonding here, okay? This is a really important graph that you actually need to be able to not only understand when you see it, but to be able to talk about it, to have a discussion about what's going on here in this graph, okay? So let's say we have 2 atoms that are about to make a covalent bond between each other, okay? So here's our 2 atoms, okay? And those 2 atoms are represented in this diagram right here, okay? These are the 2 atoms. I'm using tennis balls to kind of show this. Now, when they're at a certain distance from each other, okay, they're unable to share their electrons, okay? They have to get to the right distance between them in order for these 2 atoms to comfortably overlap their orbitals and actually share a pair of electrons between them, okay? Now, in this graph, if you look at the the y-axis, it's labeled as potential energy. And the x-axis right here is the distance, the radius, the distance between the two atoms that are about to make a covalent bond from one another, okay? So what we're going to do is we're going to follow the distance between the two atoms that are going to form the covalent bond and the potential energy that these two atoms have, okay? So if you look closely at the graph, when the distance, okay, is pretty far away, so they're actually far away, because of that distance being far away, they're unable to form that covalent bond. So their potential energy state is pretty high, all right, because they have not formed a covalent bond to share their electrons to form complete shells in order to lower that potential energy. So it's not until these atoms begin to get closer and closer that we begin to see the potential energy begin to drop, right? As I trace this line, okay? The closer those atoms get to one another, the potential energy begins to go down. Now, why? Is because as they're getting closer together, their orbitals begin to overlap now. And as they begin to overlap, they begin to be able to form a covalent bond. Now, it may not be at first a very good or very strong covalent bond because the overlap of those orbitals aren't very good yet, okay? But as they get better or closer and closer, eventually we get to a low energy minimum, okay? Or a very low energy in the dip right here, okay? Now, what that means is that we have got the best overlap of those orbitals, and the covalent bond is at its best. It's at its finest here, okay? It's very strong. The electrons are exactly the perfect distance away from both nuclei that are being shared, okay, is what we're trying to say here. So at this point, we would say the covalent bond are formed by minimizing the potential energy between the atoms at this. This is the most stable state for both of these atoms at this low potential energy state, okay? Now, at this low potential energy state, we also call the distance between the two atoms that are overlapped to form the covalent bond, we call this the bond length. Okay, now the bond length is really important concept and that we will talk about much more a little bit later. But for now, I just want you to know that the bond length is the correct distance between the two atoms that are forming a covalent bond to give it the lowest potential energy state needed, okay? Now, if I try to, so far away, right? They're high in potential. It's not until they get to that optimal bond length that they're at the lowest energy state. But what happens if I try to push those atoms closer together? Okay, what happens to the potential energy? Oop, the light went off. When I try to squeeze those atoms together to get them even closer to one another, the energy, the potential energy skyrockets, okay? Now, why does it skyrocket if I squeeze these atoms too close together? Well, it's because the nuclei are now interfering with one another. The positive nucleuses of both these atoms are going, whoa, we are way too close now. And those nuclei that are so positive are saying, this is unacceptable. And so they're gonna resist being pushed any closer. They're gonna go back to their optimal bond length. That's where they want to be. That's where they're the most stable. That's where the lowest potential energy state is. Okay. So let's review this really quick. These two atoms are going to come together and start forming a covalent bond. They're going to share a pair of electrons between them. In doing so, they're going to have full shells, right? Full valent shells. So far away from one another. They can't overlap the orbitals very well, so they're still in high potential energy states. But as they get closer and closer, those orbitals begin to overlap and they begin to start forming a covalent bond. And that's going to reduce the potential energy. But it's not until they get to the optimal bond length, the right distance between these two atoms, that a full covalent bond is formed, and it lowers the potential energy of these two atoms perfectly. All right, and they want to be there. If I try to push those two atoms any closer than the bond length, the nuclei do not like it. The positive charge hates it, and they're going to push each other away, repel from one another. Okay, so we always want two atoms that form a covalent bond to create the optimum bond length. Okay, and that's what we're really talking about here with this all-important graph. So again, you should recognize what's going on in this graph, but you should be able to have a discussion on it. Very, very, very important. All right. All right. So that is pretty much it. I want to address kind of some examples here. So let me clear this, and let's kind of finish up some things in your notes. All right, so we're going to use water as kind of an example. Now we're going to do a lot of more examples with covalent bonding. We're going to spend a lot of time with that, okay? But covalent bonds often form what we call molecules, compounds, special types of compounds called molecules. We'll get more into molecules a little later, but you can say that if it's a molecule, there's going to be a covalent bonding going on here. So water is a molecule, okay? It is a compound, but it's classified as a molecule. And water is made up of oxygen and hydrogen. They're both nonmetals. And so if they're going to bond together, they got to do so in a sharing fashion, a covalent bond, okay? The way we can represent this is I have a Bohr model of one hydrogen atom. I'm going to use H for hydrogen in both these atoms. And then oxygen is the center one with the O, okay? Almost looks like Mickey Mouse to me when I look at this model, okay? Got the two ears and the nose, Mickey Mouse. Okay, anyway, the point is that hydrogen has only one electron in its valence shell, right? And so in order to get a full shell, hydrogen needs one more. And so what's going to happen is one electron is going to be donated by hydrogen, and the other electron is going to be donated by oxygen. And so these two electrons are now being shared between the oxygen and hydrogen here. The other hydrogen is the same way. It's sharing an electron there and sharing an electron here. So what we're saying here is that we got a covalent bond that's formed here and a covalent bond that's formed here. So when oxygen binds to hydrogen in water, we form two covalent bonds, okay? And this is really what the bonding system works for water. So does it give them full shells? Well, it absolutely does. Each of the hydrogens, only needing two electrons, have a full shell. It has these two electrons and these two electrons. So each hydrogen has a full shell, okay? But what about oxygen? Well, oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And it also has a full shell. So by sharing these electrons in between these atoms are giving each one of these elements a full valence shell, and they have low potential energies and they're happy, okay? Now over here I have a model where, again, we can change the dots out, or the represented covalent bond going on with dash or hyphens. And that's what this is doing here. This is representing a covalent bond. This represents two electrons being shared, And this is also representing 2 electrons that are being shared here. And then we have our covalent bonds, okay? Remember, very important to understand, every covalent bond is only 2 electrons, a pair of electrons being shared between the 2 atoms, all right? So there's kind of our water example or analogy. I think I have some other ones here. And let's see, let's go to, let's see, okay, kind of shoot you this, but I think I have some ionic ones here, or covalent ones. Here we go. So let me share this simulation with you. So we have 2 hydrogen atoms, and both of these hydrogen atoms are essentially only have 1 electron in them. So they're not very happy. So what we're going to do is we're going to bring these hydrogens together. We're going to bring this one. We're going to bring this one. And as they get close and they create the correct bond length, they're going to then share their electrons, okay? So you can see that both these electrons are being shared between both hydrogens. And so now both hydrogens have a full valence shell, and everyone is nice and happy, okay? So I can break it and pull it apart here. Let's do fluorine, okay? Oops. Pull those fluorines apart here. Now each fluorine in the valence shell has 7 electrons, each fluorine. So if they share a pair of electrons, they now have 8 electrons in their valence shell. And you can count them if you need to. Count them up. You have 1, 2, 3, 4, 5, 6, 7, and 8 electrons for this atom. And for the other one, also you have 1, they share, so it's 1, 2, 3, 4, 5, 6, 7, and the other one that's being shared, 8. So this is our covalent bond, and both these electrons belong to both atoms as they're sharing there, okay? So let's pull those apart. Let's go to our water, okay? So with water, the oxygen is deficient in 2 electrons, and the hydrogen is only deficient in 1. So we get together and we form 1 bond, but it's still unstable, okay? This is not a stable because oxygen is still deficient in 1 electron, right? It has 1 more because it's sharing between this hydrogen, but still deficient. So I'm going to add this one, boom, okay? And what do we get? We get a full valence shell for oxygen, and we can count that, right? Let's do that. Let's count the electrons. We have 1, 2, 3, 4, 5, 6, 7, and 8. 8 electrons for oxygen now because it's sharing those electrons. And each hydrogen also has 2 electrons. 1, 2, it's got a full shell. 1, 2, it's got a full shell, and everyone is good and happy. There. All right, let's break those apart. Let's do oxygen. Now, oxygen is going to be unique because when oxygens get together, they each need 2 electrons to be shared. So they're actually going to share 2 pairs of electrons, 2 pairs. So in other words, what I'm saying is we're going to create what is known as a double covalent bond. So we're going to form 2 covalent bonds between those atoms, okay, just like that. So I'll draw this. This right here is 1 covalent bond, and this is the second covalent bond. So we actually have 2 covalent bonds between two atoms. that creates what we call a double bond, okay? Now, it would look something like this between two atoms with hyphens, is something like this, where this is representing a covalent bond, that represents second covalent bond, and a double bond between the two atoms, okay? And they're sharing. And there is 8 electrons between them. You can count them 1, 2, 3, 4, 5, 6, 7, 8. And this oxygen 1, 2, 3, 4, 5, 6, 7, 8 as well. Okay, so there's an example creating a double bond situation here. Okay, oops. Let's break these atoms apart now. Let's do nitrogen. Now, nitrogen, each nitrogen is actually deficient in 3 electrons. So when they come together, watch what happens. Whoa, look at that. We actually create 3 covalent bonds between them. Let me show you where those 3 covalent bonds are. So you form one there, you form another one there, and another one there. So we actually have 3 covalent bonds. That gives each nitrogen full shells by those 3 bonds. So really, if I was to draw this out, I would have what is known as a triple bond. So we went from a single bond, which is only 1 covalent bond, to a double bond, 2 covalent bonds, to a triple bond, which has 3 covalent bonds. But each covalent bond still has 2 electrons in it, okay? So don't forget, each covalent bond can only have 2 electrons being shared, all right? So between these 2 nitrogens, it shares a total of 6 electrons with 3 covalent bonds or a triple bond, okay? Cool, we're almost done. I just wanted to give you a few examples of all of this, so it makes sense. All right, what about CO2? Oh, look at this. So let's see here. This in the middle is carbon. What we're going to do is take the oxygen and we're going to form, look at that. We're going to form a double bond between the oxygen and carbon. We'll take our other oxygen, boom, and that forms also a double bond between the carbon and oxygen. So the way it would look like is we got a double bond, we got a bond there and a bond there. So that's 2 covalent bonds and then 2 covalent bonds here as well. So if I was to kind of symbolize this out, I got carbon with the double bond between that oxygen and a carbon with our carbon is double bonded with the other oxygen, okay? And so in this case, the carbon forms 4 covalent bonds, 2 bonds between each of the oxygens. So still a double bond here and a double bond here, okay? So that, again, we're going to go into a lot more into covalent bonding. We're going to learn how to actually build these molecules by covalent bonding them together and so forth here in future lessons. But I just wanted to give you an idea of what covalent bonding was and a little bit of how it looks like and so forth, okay? So I think let's call it good for this lesson. So study hard and review your notes on covalent bonding, and we'll see you later, okay?